In this video, I'm going to show you how to find the polar form of complex number. So let's jump into it. The polar form of the complex number x plus iy is as follows. A number r times the expression cos theta plus I sine theta for some value theta, where r and theta are defined as follows. R is equal to the magnitude of our complex number. The magnitude of x plus iy is just square root of x squared plus y squared. And theta is arctangent, inverse tangent of y over x. And remember, we're using the convention that negative pi is less than theta is less than or equal to pi for the arctangent. Okay, so that's the definition of the polar form of a complex number, and that looks kind of intimidating, so let's talk about why it is this way intuitively. So intuitively, r can be thought of as the radius. It's the distance from the origin to the complex number. So let's go ahead and draw that in on our graph, which has x plus iy. Distance from origin to the complex number, we'll label that with r for radius. Now, how do we compute this radius? Well, think about creating a triangle here. Let's drop down a vertical segment from the point down to the real axis. So that'll make a right angle. The vertical distance up from the real axis to this point is y, of course, and the horizontal distance from the origin to where the segment hits the real axis has length x. So we have by the Pythagorean theorem that r squared equals x squared plus y squared, which is where this r equals root of x squared plus y squared comes from. That's just what you get for r when you solve the Pythagorean theorem. Okay, so we know where r comes from. R is just the radius that comes from the Pythagorean theorem. How about theta? Where is theta in this diagram? Why is it arctangent of y over x? Well, theta in the diagram, that's just the angle right over here. And we see that the tangent of theta is opposite over adjacent, so y over x. Tangent of theta is y over x, so just invert that to get theta, so theta is the inverse tangent, arctangent, of y over x. Alright, so now that this makes a lot more sense using this triangle diagram, let's go ahead and convert some complex numbers to polar form, starting with this complex number, 2 plus 2i. To convert to polar form, we just need to find r and theta, so let's just go ahead and do that. R equals the square root of x squared plus y squared. And what are x and y in this context here? X is the real part, and y is the imaginary part. So x and y are actually both 2 in this context here. So let's go ahead and compute this. So 2 squared plus 2 squared, take the square root of the whole thing. So square root of 4 plus 4, which is equal to square root of 8, which is equal to 2 root 2. Alright, and then how about theta? Theta is equal to arctangent of y over x. So plugging in our y and x are both 2, so arctangent of 2 over 2, which is arctangent of 1, which is just pi over 4. So the polar form of the complex number looks like this. It's r, so 2 root 2, times the quantity cosine of theta, so cosine of pi over 4, plus I times sine theta, so sine pi over 4. So there we go. There is the polar form of that complex number. Alright, so on to the next example. 1 minus 4i is the next one. So x is 1, and then y is minus 4. So we just go ahead and compute r. R is square root of x squared, so square root of 1 squared, plus y squared, so plus negative 4 squared, which comes out to square root of 1 plus 16, which is square root of 17. And theta is arctangent of y over x. So arctangent of y is -4 and x is 1. Arctangent of -4 over 1 is just arctangent of -4. And if we punch that into our calculator, we get that's approximately equal to -1.326. So putting this all together, the polar form is r, so root 17, times the quantity cosine of theta, so cosine of -1.326, then plus I sine of theta, so sine of -1.326. And there we go. There is our polar form of the complex number 1 minus 4i. Next up, we want to express the complex number 1 over the quantity 1 plus 2i in polar form. Alright, so what do we remember about polar form? We remember that if we have a complex number, x plus iy, then the polar form is r times the quantity cosine theta plus I sine theta, where r is square root of x squared plus y squared, and theta is arctangent of y over x. But our issue here is that the number 1 over the quantity 1 plus 2i is not in the form x plus iy. So our first step really is we need to take that number 1 over 1 plus 2i and we need to convert it into the form x plus iy. And then we can finally convert it to polar form. Okay, so first let's worry about this part here, converting our complex number into the form x plus iy. How should we do that? Well, remember that whenever we've got a complex number in the denominator, we can make that denominator real by multiplying the top and bottom by the conjugate of the denominator. So let's go ahead and do that. What is the conjugate of 1 plus 2i? Conjugate, you just flip that plus into a minus. Change the sign, so get 1 minus 2i on bottom and on top. So we do that, and the result, 1 times 1 minus 2i is just 1 minus 2i. And then on the bottom, we've got 1 plus 2i times 1 minus 2i. So 1 minus 2i over, let's go ahead and multiply out that bottom. 1 times 1 is 1. And this is a factored difference of squares. The middle terms will cancel out. And we just have minus the last terms multiplied. So minus 2i squared. So this becomes 1 minus 2i over 1 minus 4i squared, which is equal to 1 minus 2i over 1, and then I squared is -1, so 1 plus 4. Let's bring that back over here to keep on simplifying. So that becomes 1 minus 2i over 5. 5 is 1 plus 4. So 1/5 minus 2/5 I. Okay, so that is our rectangular form. That's our x plus iy form. Let's write that down. 1/5 minus 2/5 I. And now we can go ahead and convert that to polar form now that we know what x and y are. So let's go ahead and compute r first. R equals square root of x squared plus y squared. So r is square root of 1/5 squared plus -2/5 squared, which is equal to square root of 1/5 squared is just 1 over 25, and then 2/5 squared is just 4 over 25. So this is square root of 5 over 25, and 5 over 25 is just equal to 1/5, so square root of 1/5, and we can apply the square root to the numerator and denominator separately. So square root of 1 is just 1, square root of 5, just square root of 5, and let's go ahead and get that root out of the denominator. Let's go ahead and multiply by the same thing on top and bottom by root 5 and root 5. So 1 times root 5 on top, that's root 5. And then root 5 times root 5 on bottom, that's just 5. So this is our value of r. And then how about our value of theta? Theta is arctangent of y over x, so arctangent of negative 2/5 over 1/5. Let's simplify that a little bit. So this is arctangent of, if you multiply the top and bottom of this fraction by 5, you can cancel those over 5s out, and you just get negative 2 over 1. So arctangent of negative 2 over 1, which is equal to arctangent of negative 2, which, using a calculator, is approximately equal to negative 1.107. So that's our angle. And finally, we can write the polar form. Polar form is just r, so root 5 over 5 times the quantity cosine of the angle, so cosine of negative 1.107 plus I times sine of the same angle, negative 1.107. So there we go. There is our polar form. Lastly, we want to express the complex number 2 times the quantity cosine of pi over 3 plus I sine of pi over 3 in rectangular form. So we want to take this form, which is in polar form right now, and turn that into x plus I y, rectangular form. And to do that, all we really have to do is evaluate this expression. So let's go ahead and do that. 2 times cosine of pi over 3. What's cosine of pi over 3? It's just a half. Think back to the unit circle. So a half, then plus I times sine of pi over 3. And what's sine of pi over 3? Sine of pi over 3 is just root 3 over 2. So now we can go ahead and distribute this 2 over. So this is 2 times a half, then plus 2 times I times root 3 over 2. And the 2 cancels with the 2 in the denominators. So we just have 1 plus I root 3. And there we go. There's the rectangular form. So now we know how to find the polar form of a complex number. And this will be very useful to us in the future because it'll provide an easy way to take products of complex numbers which are expressed in their polar form.